Good afternoon, ladies and gentlemen. The conference will be commencing shortly. We request you to present in the conference area in hall 3.
Good afternoon. Exhibitions, ladies and gentlemen, we'd like to announce that the conference on artificial intelligence for the manufacturing is about to start. People are going to register and interested to learn the session in Hong. Thank you.
Good afternoon, ladies and gentlemen. The conference is on the field. Request to all to please come to the conference area. Now proceed.
for gathering at the conference today. I would like to invite Mr. Vinod Sachidharan from HITEX to give the welcome address.
Good, and a lot of knowledge sharing would happen on this platform. Let me welcome Dr. Shailesh Kumar to give the keynote address. Shailesh Kumar, sir.
Fair, I guess, and I've kind of grown up with the field of AI and data science, and what I want to do today is kind of talk about how AI has been transforming mankind and all the different verticals, and how do we think about AI as a field, like we think about manufacturing, engineering, physics, mathematics, science, network, all these as full-fledged of AI. So this is the 8 layers of AI we will talk about, and how these layers help each other to build a full AI capability for any vertical, whether it is retail, telecom, manufacturing, and all that. Alright, so let's look at the context we are in today. So the context is we live in a very interesting time where we have convergence of a lot of technologies coming together. And the real magic that is happening around us is because of this convergence coming from there. Sorry. So now, when we think about the convergence of all these technologies, that is where the magic is happening. Because we have devices, because we have internet, because we have cloud, AI is now going through the next revolution, and it is actually reaching the masses, right? So that is the next version of AI because of all these other technologies. Yeah? And along with these, we have things like AR, VR, 3D printing, metaverse is coming, and all of that. And it has done amazing things, right? We have discovered fire and wheel, we have invented the internet, we are now going to the Mars, and we have done all these beautiful things. And in spite of all that, he is saying AI is still the most important thing mankind has ever done. So that tells you the power of what AI is. But if I ask a factory worker, or if I ask a farmer, or if I ask a teacher, or a student, or a patient, they don't see AI that way, right? So what we have is a promise, which is, hey, look, we have built great search engines, we have built great, this is the next 20 years potential of AI. Yeah? And that's what this is a promise statement, this is not an achievement statement. So what he's saying is, in the next 20 years, we are going to see AI becoming the most potential thing that we have ever done, right? So that is the theme, that's how I read this statement. Now let me talk in another dimension. If I think about the 5 I's that make a great product, so if you look at the great product we are surrounded by today, right? So if you have Google Search, Google Maps, LinkedIn, Facebook, Ola, Uber, because all your Gmail, all your LinkedIn, all your videos are stored somewhere else, right? Infrastructure, so now you can scale anything. Google can do 5 billion queries a day, Ola can run 100,000 taxis in a city, Swiggy can deliver 1 million meals a day. Scale is now easy, right? And we can do scalable manufacturing, scalable supply chain, scalable whatever we want, right? That is the first time. The second I is the interface. Today, if you think about how the third I came recently, which is about the intelligence, right? So it's not enough that Ola Uber is a beautiful and scalable product. It must also deliver a nearby car in real time, right? Google should give me the right search result. YouTube should give me the right recommendations. LinkedIn should, Google search result comes within 300 milliseconds. Ola Uber has to come within 5 minutes, otherwise you cancel. And pizza delivery is 30 minutes. So everything is instantaneous. Now we are in a time-bound mindset. And manufacturing will also go through this transformation. We are going to have just-in-time manufacturing, 3D printing is coming. So there are new revolutions again with the same instantaneous mindset that will come, right? Car maintenance has a great infrastructure by itself, traffic infrastructure is great by itself, but when you combine all this and integrate them into a connected car ecosystem, then it becomes a integrated product, right? So today we have all the parts here, but of AI, so we have some context around how to think about AI in any domain. So this is one kind of a workflow. When things are running normally, you don't need to do anything, but when something goes wrong, you need to work on that. So this is one kind of a workflow of AI, where what we do, so let's say I'm applying this to retail or telecom or manufacturing or refineries or media, any vertical, I can use this workflow. So the first thing is we monitor everything. So the AI is built on this idea that you have stimulus data coming in all the time. Doing this, I think dashboard is one of the graveyards of data, because there is nothing you do about it, right? Dashboards don't help you improve your business. What you don't need is give me the average, the total. That's not what you need. What you need to know is what needs attention. So in a telecom system, if a cell tower is down, I need to know that cell tower is down. In a retail, if a delivery is not happening on time on a certain apartment, then that's what I need to know. I don't need to know the average delivery time of a city. That's it is wrong. And why is it so? I need to be able to generate actions. And once I generate action, I need to execute actions. And we separate, this is called the mind-body separation. The mind generates the action, the body executes the action, right? So we have execution systems and a brain which tells you that increase the temperature of this unit by 5 degrees, right? That is coming from AI, but the system that does the temperature increase is a different system. So we execute. Can a smart city follow the same process? Can a healthcare system follow the same process? That is the challenge. So we understand what is intelligence. We need to now migrate it to all the systems. Yeah. So now let me start with the ASTANG AI part. I just wanted to give that background. So when we talk about AI DS, we talk about it from many perspectives, right? So one is, what are the different types of tools that AI provides? That is one perspective. Then we talk about what are the different types of data AI can be applied to. That's one perspective. What is the process of AI, how to build up and deploy a model, that is one perspective. What are the domains in which it can be applied is one perspective. Now I will talk about AI from a completely different perspective, which is what are the different layers or in the architecture of AI. So if you know the networking architecture, right? If you look at the internet and how the networking layer works, there are 7 layers in the networking stack, right? The lowest layer is the bits traveling on the hardware, which don't know whether it's a WhatsApp message or a YouTube. It's just a bunch of bits at the lowest level. And at the highest level, we have application layer, right? So in the networking, a very vertical centric field, and the same principles can be applied across all domains. Alright, before we go there, I want to talk about the evolution of products and what are the next generation products which are going to challenge and need a different way of thinking about AI. So if I look at product 1.0, these are the physical products that come with programmed intelligence, right? So if I have let's say you say if the RPM is going above this or temperature above that, shut it down, is a rule you can encode into a physical system. And it will not built with programmed intelligence. They improved over time. Google search is still improving. LinkedIn is still improving. And they are improving because all of us in the planet are using them, giving them feedback data that look for this query, you are giving me these results, but most people are clicking on the third result, not the first two. So from that feedback, Google is learning how to improve search engine. So we understand that second generation products taught us how to use feedback data to improve the system. Now we are heading into third generation products. So third generation products are going to be the products of the future, right? They are known. So how do we take our thinking from one drone, one farm, one fertilizer, one farmer to agriculture ecosystem of the country? What does that mean? It means the entire supply chain, entire demand forecasting, entire supply forecasting, entire policy decisions, entire supply chain of chemicals and fertilizer thought as a single product, not as 10,000 individual things. This is the integration mindset that we are heading. Same thing in health. So what are the characteristics of these systems? What makes a complex system? And I'm going to compare it to Google search. So now think about a complex system, let's say a refinery or a telecom system or a smart city, right? It is made up of billions of entities, of hundreds of types of entities, right? Google is made up of two types of entities, queries and documents. But a telecom network is made up of people on the ground, cell towers, SIM cards, person who is, installing your thing, all of that, right? So billions of entities. Now we are heading into a completely different ball game where we say that, look, to run a telecom or to run a retail or to run a manufacturing, you have so many interactions happening all the time, right? Parts are failing, you need to order, you need to do controls of everything, you need to think about supply chain of raw material, supply chain of finished product. So you need to think about many, many things, and all these interactions are happening simultaneously. There are hundreds of metrics that are interdependent on each other. It's not that Google search is doing, let's say, increase the click-through rate on the first result. That's their single metric. But right, this is a complex system. It's like your body is a very complex system. It is not doing one thing. I'm not just giving a talk right now. My body is doing 10,000 other things simultaneously I'm not aware of. That is a complex system. Yeah. So how do we think about such systems and do that? So this is the framework that we have come up with. So let me see. Yeah. So now I'm going to talk about the 8-layer framework, and the layer 0 is the layer that you definitely need, which is what I call a digitization layer. Today there are a lot of domains where data is still not digital in nature, right? Today when we are ready for AI. So digitization layer is a prerequisite to AI layer, right? Now let's talk about the 8 layers of AI. So the first layer is what I call interpretation layer, which basically interprets all the data into a higher level semantics. So if you get a time series, what does it mean? If you get an image, what does it mean? If you get a gene sequence, what does it mean? If you get a video, what does it mean? How do you interpret that? Yeah, that is the first layer. The second layer is what we call causality. And if I tell you 5 variables, the first thing your brain does is what is cause, what is effect, right? So causality is a very important. Now today in AI, predictions are not enough. We also have to think about explanation of that prediction. So you cannot tell a patient through an AI doctor that you have this disease. You have to explain. You cannot deny a loan to a person and say, a loan denied. You have to explain why, right? So explanation is now part of prediction. The next layer, and this is where I bring it into the engineering side of things. So the next layer is controllability thinking. So causality thinking is one kind of thinking. Control optimization, then you can do adaptation. So these are the 8 layers we will talk about, and hopefully this will give you a broader perspective on AI than what we have seen so far. Yeah? All right. So let's look at digitization layer. Layer 0, it's not part of the AI stack, but it's a must. So today a lot of data is still physical in nature, right? The printed books, the printed receipts, the printed invoices, the printed whatever. And now we have digitization mechanism to scan everything, take a photo, interpret the photo, and OCR everything. Google or a PDF of that is not digitization. Understanding what is inside the document, storing it in a database is digitization. Yeah? So we need to understand the document, not just scan it. And that is true digitization. Now, where are we applying this today? So if you look at, there is a whole field called visual document processing. And the job of that field is to take physical structured documents like invoices or, product descriptions and all that, and digitize it, store it in a database, and in a company meant for human consumption. An engineer built it. Another engineer who is going to build the plant or maintain the plant is using it. There was no thought about AI using this ever. Now if AI has to maintain your plant, this data has to be digitized, right? So for that, how do you extract all the tags and labels, all the instruments and their shapes, all the sensors that are there, all the connections between the whole thing? How do you extract that automatically at scale so that you have a PNID understanding system from a AI perspective, and then you store this information in digital. This is a big transformation that is happening, that, the PNID document was never meant for AI to consume, only humans to consume. So this is the first time we need to think about this transition, that whatever we have built for ourselves is putting human in the loop of decision making, which is not scalable for a complex system, right? Like a security guard has to watch the videos and tell there is a security incident. Again, a human is in the loop. So the goal of the next generation AI is to automate all these processes. Yeah. All right. So that was the data, which is a low-level data converted to high-level semantics is interpretation. It doesn't matter what domain, what data type. It doesn't matter. So if I give you a gene sequence and you can tell me this person will have Parkinson's at 80, that is also interpretation, right? And what Alexa does when it hears your voice and says this is what you are saying is also interpretation. So we understand it's a horizontal layer, and the way human interpretation system works is when you listen to a speech audio, you don't interpret one thing. You interpret all things that can be interpreted from that data. Inspiration for the interpretation layer, if I look at all AI is inspired by human intelligence, right? And human intelligence was not possible if we did not have our 5 sensory systems. And each of these sensory systems is an amazing interpretation system that has evolved over billions of years in a biological environment, right? So today we can interpret the pixels into objects and images that are falling. We can interpret the sound and say this is the noise, this is a bird chirping, this is my wife calling, whatever it is, and all these. And language call center when a customer is calling, or you can use it in education apps and all that. Another kind of interpretation is song interpretation. So today, companies like Spotify, what they have done, they have converted a song into these 9 beautiful dimensions. So they can take any audio signal of a song, low-level data, and convert it into a 9-dimensional, high-level semantics. This is interpretation of a song, and you like a song not because it is by somebody, written by somebody, sung by somebody. You like a song because it falls in some space in this 9-dimensional space, found kind of interpretation. So you can convert any piece of text and say, what do you mean by the word apple here? Is it a fruit or a company? That is interpretation called word sense disambiguation. Another kind of interpretation we do is when we read a newspaper or a magazine or an article, what do? We don't remember the text afterwards. What do we remember is the knowledge it contained. What were the entities in it? What was the relationship among those entities? That's what we really remember. So this is also interpretation. One form of data, which is a sequence of words, convert an unstructured piece of text written by a human in a very wrong way, misspelling, wrong grammar, and you can still tell that all the green sentences are similar and positive sentiment, and all the red sentences are similar and negative sentence. This is the level of sophistication of text interpretation today, that even if the grammar and all this is bad, AI can still understand, positive, negative sentiments. Yeah. Now let's talk about deeper interpretation. So if you think about interpretation followed by another interpretation. So for example, when we talk to Siri, Alexa, I need to find out all these elements, and how do I do it from the text you are giving me? How do I know indigo is not a color but an airline? How do I know what is next Monday? And how do I know what is early morning? Yeah. So this is also interpretation. So this is text interpretation. Another deep interpretation idea is, a lot of times we do sentiment analysis. Everybody wants to know what people are talking about them on the internet. Is it a positive or a negative sentiment, right? What are my reviews? Now there is no such thing as a positive review or a negative review. You can be positive about some aspect and negative about another aspect for the same entities and interpretation of that. Now people are building systems where they can take a picture of your face and tell what disease you have. Because if you know somebody very well and you have seen them again and again, and suddenly one day you see them very pale, you can tell that something is wrong, right? And we live in a selfie generation. So my phone has all my previous images. So when I take a next image, it can tell, you see? So interpretation of face to disease is possible. Similarly, on the right side, today we can do this much. But tomorrow what we can do, we can even tell you what is the breed of the dog, what is the breed of the horse, what is the number plate of the car, what is the make and year of the car. They actually want to go to every scene and interpret every scene and say this scene in this movie, what is the interpretation of this scene. So they want to know who are the people in this scene, what is the genre of the scene, not the movie. So this is a musical, right? And then what is the location, inside, outside, what are the actions they are doing, what is the sentiment of that scene, right? And today that is possible, and this is deep interpretation of content. So now with content interpretation, like we did songs, now we are doing movies also, right? And you have visual data and audio data. Is to define the dimensions along which you want to interpret something, and then what are the categories within that dimension. Medical science is now catching up on AI big time, right? Today we can interpret images like X-ray, MRI, CT scan, PET scan, almost as good or better than a human expert can do. Yeah. Now imagine what will this do? It will scale up our ability to do this. Within a few seconds, AI will generate a report, and you can do millions of such reports in an hour, as opposed to waiting for 3 hours for one pulse of just one layer, interpretation layer, and it is very broad. It can work across different types of data. Now let's talk about causality layer. Right? Now I'm going to use this projectile example to go through the rest of the layers. So we all studied projectiles, right? If you throw this, what will happen? Now when I look at a projectile in the physics world, what do? We think about all the quantities. Height, angle, maximum height, time, all of that. What do we do with all the 7-8 quantities? We put them into 2 buckets. What is a cause? What is an effect? This ability behind that, right? Or what is the behavior of a customer? What time he makes more phone calls? Where does he spend most of his time? It is what it is, right? Or what are the preferences of a customer? Or what are the sensitivities of a customer? So this is the zero of causality. That means there is no causality. It is a law, therefore it is. So you observe. Now let's talk about the different flavors of causality. So the first type of causality is what I call multi-factor causality. That means if you have an effect, right, and you can have multiple causes for the same effect. So if disease is the effect, the doctor wants to know, to build a causality layer very deeply and think about which factor is causing this particular cold drop or this particular disease. Okay? Another kind of causality is what we call cumulative causality, where things add up. So for example, in Ola Uber world, if you think about the total demand of Ola cab in this part of the city at this time of day, what is the total causality? That is a number. What are the factors causing it together? Add up. So of multiple things adding up, right? So you say what are already there, what are incoming, what are outgoing, and all of that, cancellations and all that, you add that up. So we understand this is the second flavor of causality. Another flavor of causality is dependence-based causality. So now this is an education example. Imagine that you have a student A who is doing very well in concept P, medium in Q, and very bad in R, right? And now you have a causal structure between what concept can be taught if what concepts have been mastered. This is called mastery learning, right? You cannot just keep this. You need dependent structure between things. Another form of causality is what we call temporal causality, right? So time-based thinking. So if somebody has bought a printer in your retail world, right, what is the likelihood that he will buy a cartridge 3 months from then versus just randomly giving cartridge coupons to everyone, right? So can we think in event-based causality, whether it is retail, whether it is agriculture? If I have grown this crop on that day in this part of the country where this is the soil, this is the weather and all that, what is the likelihood time when I will see a harvest? If I have a temporal causality, which means just because it is winter, something will go up, blanket sales will go up. Just because it is monsoon, umbrella will go up. There is no prior event, right? So these are different flavors of temporal causality. Another very important kind of causality is what we call structural causality. So the idea is now you have a complex system like a refinery or a manufacturing unit or a smart city or a human body. It's a complex structure. And if something fails, so that is structural causality, how things propagate through the structure. Yeah? Same thing in traffic. If there is a traffic jam here, what else is going to happen in the city? These are all connected ideas. I'm trying to make sure that we understand the breadth of this thought process, and now you can start to see how you can apply this to your world. Now this is a very important slide. One of the most important skill sets in a complex system thinking is deep causality. So now let's take Ola Uber example. So imagine that Ola Uber is giving some incentives low, cab guys is sitting there, no work. You understand? So these are dependent. Then what does that lead to? How many people got a cab? Fulfillment. How many people got converted? If the prices were too high, people start cancelling. So conversion goes down because prices are high. You see the dependent structure between everything. Yeah? And then customer experience is poor because you are calling cabs from far away. Right? Your efficiency of the platform is low because a lot of drivers are sitting idle. What does that lead to? So that leads to customer metrics like engagement, output side. This is an important skill set our data scientists don't have. And our domain experts don't have. Why? Because they work in their silos. They don't think end to end. And that is the new kind of thinking we have to develop. Yeah? So that was layer 2. Now layer 3, prediction. So I know what is cause, what is effect. Can I quantify the cause and effect? How much of this will lead to how much of that? Right? So quantification of cause and effect is prediction. So I learned the causal, visited the doctor, right? Or this could be, manufacturing alarms that are coming at different time rates, right? So you have a timeline, you have events happening on a timeline, and you are supposed to predict a future event given all the past events, right? This is a prediction mindset altogether. So now how do we do it? We say, okay, here is my observation window. Look at last 6 months of data, 3 months of data, 1 week of data, whatever. And this is the prediction date of a future prediction of a customer from my bank, or I'm predicting the failure of a crop, or I'm predicting that a scam. So I'm predicting a negative event, and what can you do to intervene is the first reason why we build prediction models. Yeah. So this is the first reason we want to predict, so we can intervene and avoid a wrong outcome. So this is the first reason why we build prediction models. Second reason why we build prediction models. Now here, let's say we are predicting the stock market of value of a stock, or a demand forecasting of how much iPhone is needed in this prediction for optimization. Third reason why we do prediction is to personalize the decisions, right? So now Netflix knows what kind of movies you like. A new movie comes, should I show it on your home screen or not, is based on a prediction that will you like it or not. I am predicting that, right? So that's also a prediction. Let's talk about the fourth reason we build prediction models. There is a subtle reason why we build prediction models, which is the following. So now let's say in the telecom world, one call drop happened, and I know what are the possible causal variables. Network load is high, indoor, out, suddenly, because you are making a phone call, right? So I cannot intervene, I cannot optimize in real time. Why do we build such models? We build such model. This is the fourth reason why we build prediction model, is to learn the causality differently in different contexts. So I want to learn why in this part of the city call drops are happening at this time of day, and in this part of the city call drops are happening in this part of the day. The call drop probability is the same, but the reason is different. And if the reason is for that prediction, yeah? Okay. Now same thing applies to refineries, for example. So today I am running a refinery with certain inputs, I get certain outputs. Tomorrow I am running the refinery with certain inputs, certain outputs. Tell me the why. Why did naphtha production went up and jet fuel production went down today when it was high yesterday? Why? The why is very important, and we build prediction model to explain the why also is important. Yeah? Alright, so we understand the explanation layer, right? Prediction to explanation. Now we pivot into the engineering, and one that I cannot control, which is only observed. Gravity, wind speed and whatever, right? This ability to distinguish between controllable and observable is controllability thinking. Causality thinking is to list all 6. But controllability is what subset of those I can control. This is a very important transition when we go from prediction systems to optimization systems. Yeah? Okay. So now if I think about prediction, I will think like this. But when I think about controllability, I will think the input is not just one vector of input. It has two parts. Second phase of AI. All right. So now for some examples. So if I look at telecom or refineries, I can think of this if I don't think of controllability. But when I think of controllability, I say, look, the feeds are given to me. I don't know how to control them. They are coming from the previous unit. But what I can control today in this unit is temperature, pressure, and catalyst. Right? So this is all the handles you have to optimize your plant. You cannot go to the feeds. And that thinking is very important. And how do we build these models today? So we build hybrid digital twins. So we have the physics. What is the customer preference is I cannot control, but I can observe. I know what kind of things he has bought at my store. So I know he likes this brand. He likes this color. So I know the preferences. I know what the competitor is doing. He has lowered the price on iPhone. So I know what the competitor is doing. I know what the customer is preferring. I cannot control it. I can observe it. So I can put it in my model. What I can control is what is the discount, what is the messaging, what is the channel, and what is the timing. Control. I cannot ask him to go out of the house and then make a phone call, or stop the car and then make a phone call. Those are observable but not controllable. What is controllable is what is the coverage I am providing in that area, what is the interference on his cell. So that is controllable. Yeah? So that is controllability thinking. And now I can do deep controllability. So if I am seeing a lot of churn in my telecom network, I need to ask why. So I can go back and say behavior and usage I cannot control, but call drops, call quality, and throughput I can control. How do I control them? Again, I go important slide, because this skill set is missing today. Today, data scientists don't think of an ecosystem of models. They think of one model and they're happy. That's what Kaggle competitions have trained us to do. Build a model, get a rank, you're happy. But when you have to put a whole system together, you have to connect the dots. So what do you have to do? You have to think in terms of business metrics, churn, customer experience, call drop, throughput, then operational metrics, right? Interference and coverage, and then operational actions. Unless we are able to build, will it go? If I throw this much, will it go? We simulate a lot and then we perfect it, right? If I'm in this position and there, how do I throw? So the same idea is simulation. We do a lot of simulations to get there. Now simulation is going to be a very important skill in the AI world, more important than deep learning, right? And it's coming from another industry. So what is simulation really? So I have built a model which is very good. Accuracy is very good. I know what is controllable, what is not controllable. Now I can change the slider. So now I can say, if I give this discount, what will happen? If I give this discount, what will happen? Will the conversion will blow up? So you need a digital twin of the plant where you can, do simulations, and not only at one unit level. Across all units can you simulate and do a global end-to-end optimization and then decide what to do. That is the challenge. Yeah. So controllability thinking is y is equal to a function of observed and control, but the ability to repeat this exercise for many observed variables, many control variable combination, what are the output combinations? Create that data, use it to build a digital twin, right? Because you need to result of the last unit, but 250 units that led to that output, right? A complex plant is not a single layer. It has many layers. Can you jointly optimize all of them? That is a challenge. But if we are only siloed thinkers, we'll only optimize our own unit, but we'll not do end-to-end optimization. So this is where the holy grail of refinery is. Yeah. Now what does it mean in the telecom world, for example? So now I can can you now optimize? Because simulation is also not the goal, but it's a journey in that direction. So now you want to actually not simulate. What do you really want to do? The real question is not that if I put this input, what will be the output? That's not the question. The real question is, I want to maximize the conversion rate of this customer. What control variables should I apply? what discount should I give, what messaging, what channel, what timing, because observed I cannot control. But the control variables I can control. So in the 4-dimensional space of control variables, can I say what is the best so that I can maximize the conversion. This is the decrease interference there. How will that happen? I have to add capacity here, change tilt there. So this ability to drive a business metric all the way backwards, not forward, is the core skill. How do we go from business metric and say reduce churn, therefore do this, 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 and your churn will reduce through layers and layers of causality. Yeah? So this is what we are building now, end-to-end optimization of a refinery. We take a lot of data, we look at the cost of crude and all on one side, and the cost of output products, and then we try to do end-to-end optimization of the refinery. Are now different. So now you need to re-optimize, and that is our adaptability, right? So now if this is done, but let's say the customer preference has changed. Now he doesn't like one brand, he has changed to another brand. Or competitor is doing something different. What do you have to do? Do you have to train the model again? No. Causality is still the same. Optimization you have to do again. Now the same offer is not going to make sense. He has moved on to another brand, right? And we have observed it. So again, we re-optimize when the green things have changed, which is observe the Y needs to change. What should be my C again? Can you re-optimize again and again and again? So now if a new crude has come, you have to re-optimize the whole refinery, right? Or, you have added more cell towers in certain locations. Now you have to re-optimize your entire telecom network. That is adaptation, right? Or if a network load of a city is different in the morning and evening and afternoon, you have to re-optimize your e-tilt every time because the city is a dynamic entity. I don't know if you have time for questions, but no questions. You can connect on LinkedIn and we can chat more. Yeah, thank you.
Thank you very much, sir. That was a tea break now, and we're going to set up the stage for the panel discussion that follows.